Now what we are going to look at is the fundamental flexure formula, also known as the bending formula, which gives you a direct correlation between the normal stress and the applied bending moment. Now we have already seen that at every section of this beam that is bending, the normal strain, it varies, and the normal stress varies linearly from the neutral axis as you go above or down, right? We have not seen that how these strains or the stresses are related to the bending moment. The flexure formula essentially gives us that, right? And to derive the flexure formula, we are essentially going to make use of the first two equations of statics. The first equation of statics essentially is the force equilibrium, and the second equation of statics is the moment equilibrium. Now before we go ahead and write the equations and solve and derive them, and what you will see comes out of the first equation of statics is essentially the location of the neutral axis. Now can you imagine that when this beam bends, right, so we have the top part, the length, which is contracting, the bottom part which is expanding, and in between you have this neutral axis somewhere between the top and the bottom, which the length remains the same. Now can you and length remains the same, and also the stresses and the strains are zero. So can you intuitively think that along which line or along which point does the neutral axis lie? Yes, you probably can guess it from intuition that it lies about the centroidal axis. Now the first equation of statics, or the force equilibrium, gets that, and the moment equilibrium essentially helps us get closer to the flexure formula that is there. Okay, so let's start with the first equation of statics that is there, and then we'll look at the second equation of statics. Now the first equation of statics, as I said, is the force equilibrium, and we are not going to write and derive all the single equations, because these are essentially precursors to getting to the flexure formula. So we'll quickly skim through those. So as you can tell, the force equilibrium is essentially that if we take this cross section, see, our beam is bending, and as long as it's prismatic, it does not have to be rectangular. We're looking at a prismatic section. The section itself is in equilibrium, and say at a distance y, my stress is sigma x that you have over here. So the force that is acting, force is stress times area, that is sigma x times dA. Now if we integrate that over this entire cross-sectional area that is there, that must be equals to 0, because the section itself is in equilibrium. It's just bending, section itself is in equilibrium, it is not translating anywhere. So if we have to expand this formula that is over here, remember this sigma x, which we have already seen from the strain from that last lecture, that sigma x is nothing but the modulus of elasticity times your curvature times y times dA equals to 0 over here. So this expression essentially leads to this particular relationship, that is y dA must be equals to 0. So what does this essentially mean? This means, and this is over again the entire area that you're looking at, right? This essentially means that the first moment of the area with respect to the z-axis. So you are calculating this about the z-axis over here. So that is equals to 0. So that means that z-axis, the point about which you are making the forces 0, must pass through the centroidal axis. So that means that since the z-axis is the neutral axis, so the neutral axis must pass through the centroidal axis, which exactly matches our intuition that the neutral axis must pass to the centroidal axis, and along the neutral axis we do not have any change of length, we do not have any strain as well as the stress. So this is one of the first from the first equation of statics we get this important observation. Now let's take a look at the second equation of statics that is there. Second equation of statics, as we mentioned, is this is the moment equilibrium that we have. Now similar to the force, now if you take the moment, we are looking at the same section that you have over here. Now previously we did that your summation of sigma x summation of sigma x dA was equals to 0. That was the force equilibrium. Now we are calculating the moment. Now remember, this moment overall must match this bending moment that is over there. So that is given. So as a result of these forces, now from this force distribution, can you sort of tell, because from these compressive forces you can have an equivalent compressive force, from this tensile you can have an equivalent tensile force, and they will be separated by a distance, and that will give rise to this moment that is there. But leaving that aside, if you go ahead with the basic fundamentals, what you have, your sigma x times dA times this distance y, that is the moment of the force which is acting on this small area over here. as similar to before. If you integrate over this entire area, and if you substitute this sigma x that you have over here, right, because sigma x we know is minus of epsilon minus of this curvature, which is kappa, times the epsilon times y, so y becomes a y square. So eventually if you simplify this eventually leads to this particular relationship over here, and this is important. This will lead us to the Flexure formula that we have over here. Now from this relationship, what you can tell that this relationship also sort of leads you to the relationship that your curvature, that is kappa, right, is 1 over your radius of curvature is equal to m divided by ei, right? Now what is this I as derived in this relationship? Because if you see this relationship over here, eventually it simplifies to integral of y square d, and this integral of y square d is nothing but I. So this is nothing but your area moment of inertia, if you remember from what you have studied in +2, and I will give you some other references as well. This is the area moment of inertia, and this you are calculating about the z-axis in this particular case, right? So it is IZZ if you want to say. So this is about the z-axis over here. So you get this relationship that you have over here. Now this relationship is essentially going to lead you to the Flexure formula. So let's go ahead and see that how the Flexure formula is derived. So let's keep this relationship in mind. Let's go ahead and maybe write this equation as well in the next page. And this is the relationship again rewritten over here. This is what we just wrote in the previous page over here, that remember, this is again our positive convention for the moment, this is the negative convention for the moment and the curvature, positive convention for the moment and the curvature, and it also tallies if you see, right? Because when you have this positive moment, you are seeing the positive curvature which happens, and you see kappa comes out as positive. When you have a negative moment over here, your kappa will come out as negative. Over here the negative curve. So if you put m as plus, kappa comes out as plus. If you put m as minus, kappa will also come out as minus over here. Now let's take this relationship ahead and write the Flexure formula. Remember, when we started this lecture, we said the Flexure formula gives you a direct one-to-one relationship between the stress and the moment, right? So let's go ahead and write maybe this relationship which we just saw, that our kappa was equals to m divided by ei. This is what we just derived in the last page, right? Also remember, from our expression between the stress and the kappa, what was that relationship? That was sigma x was equals to minus of kappa epsilon y. Because remember, the strain was your y times kappa. So your stress from Hooke's law was E times y times kappa, which is slightly rearranged. So kappa times E times y. Now, if you take these two relationships that are there, this one and this one over here, and if I take this guy kappa and I put it in this one over here, now using these relationships, the left and the right, I can write the famous Flexure formula as sigma x. Let me just rewrite that again, that sigma x is equals to minus of m y by I. So this is your Flexure formula. So now you see that from this formula you have a direct one-to-one relationship between the stress and the applied moment, and it's pretty intuitive if you think about it. For example, we said that at the neutral axis level, that is at y equals to 0, you have no stress and the no strain, whereas if you are moving away from the neutral axis, if you are losing at the y top or the y bottom, you will have the maximum and the minimum stresses. Now depending upon the moment, of course, it will be either the maximum tensile or the maximum compressive, but you get the overall idea. Now before we move on, one more thing which I would like to note is this term EI, which we will see is mentioned in many of the textbooks. Can you guess what is this EI called? Now remember, when we studied axial load, the denominator AE was axial rigidity. When we studied torsion, we had a JG, which was the torsional rigidity. Now EI, see, the higher the value of EI over here, it is, the higher, the lesser will be the value of kappa. So to get the same amount of kappa, you have to apply more and more amount of moment for a section which is a higher value of EI, right? So this product of the Young's modulus E and I, right, which is the area moment of inertia, is known as the flexural rigidity. This is an important thing to know. It's an important terminology. In many books, they just give you the flexural rigidity and you are supposed to know what that is, flexural rigidity. So now that we have the flexure formula, at our disposal, let's go ahead and take a look at, a couple of examples of how it works out to be. So essentially something like this. So we have, see, this is a beam. It can be rectangular, can be circular, prismatic. That's all. Only thing that matters over here, see, the shape of the section, whether it's rectangular, circular, trapezoid, or anything, comes into play when you compute the I, the moment of the area moment of inertia, right? And the numerator just depends on this distance. So here you see the maximum stresses, sigma 1 and sigma 2, happens at the top and as at the bottom over here. So C1, there you have the maximum compressive stress. Now this is also an interesting page because here it shows that, this form, you see this negative sign over here. So if you put C1, since we said that Y going from here to the top is positive. So if your moment is a positive bending moment, this is positive over here, C1 will be positive. So your sigma 1 comes out as a negative. So that means you have a compressive stress, right? As opposed to when you are going below over here, M is positive, but here C2 is negative over here. So overall it becomes a positive. So that means your sigma 2 that you get over here is a tensile stress. Now look at a correspondingly opposite kind of a moment. If you have a negative moment, the same thing holds, because in the negative moment, say you are going up, so you expect the sigma 1 to be positive, right? But your M itself is negative, so you put a negative M over here, so that becomes negative becomes positive, and your C1 is just C1 and you're going up is a positive C1, so your sigma 1 will come out as positive in that particular case, right? And that is a tensile stress, and similarly your sigma 2 will come out as negative. Now one important thing to note here is that often when engineers do the design, usually they're given a designer's handbook, and I will show you a couple of pages of that one. The designer's handbook essentially has these values over here, because see, at the end of the day, you're looking at a section. So the characteristics of the section which you should consider, or which should come across your mind to calculate the maximum normal stresses at the top or at the bottom, is how the section is, the shape of the section, rectangular, circular, trapezoid, or anything else, right? So that dictates your I, and also the maximum stress depends upon the distance, right? Like the top and the bottom. So usually these two quantities that you see over here, this guy, right? These two guys, they are usually clubbed together in one single unit in designer's handbook, and that is known as the section modulus S, which is these two guys over here. The section modulus essentially tells you, see, your I, regardless of whether you're looking at the top or at the bottom, I is same. I just depends on the section. So I divided by C1, that is I divided by this top distance, and I divided by C2, they are known as the section moduli. So you have two section modulus for every section. So it is just the ratio of the moment of inertia, the area moment of inertia, to the distances from the neutral axis to the top and from the neutral axis to the bottom. So these are the two section modulus that are there, right? But at the end of the day, in a nutshell, so overall in a nutshell, your sigma, if you just write in for the magnitude, if you just considering the magnitude, your sigma is nothing but the mod of sigma is nothing but the modulus of my by I, where y is the distance from the neutral axis, and so this sigma is positive when it is tensile, right, and it is negative when it is compressive. If you are too bogged down with the signs and what is positive and what is negative, no need to worry about it. You just calculate the modulus, you just take the respective distances, and from your intuition, from how the beam behaves, you tell whether the top is in compression or the bottom is in compression, or the top is in tension or the bottom is in tension. As simple as that, right? And accordingly, if it's a compressive, you just put a negative sign. If it's tensile, you just put a positive sign. Very simple. right? Okay, all right, so let's just go ahead and look at some of the very common kind of sections. What are the most common types of sections in beams? Rectangular section, circular section. Let's just write a couple of tidbit formulas for those. For example, if you have something like this over here, for the rectangular beam, you know that your I is essentially, in this particular case, is 1 by 12 bh cube. The unit of I is is distance raised to 4, so mm raised to 4 or meter raised to 4 and so on. And your section modulus is what? Here S1 and S2 is the same, because it's a rectangular section. Your neutral axis is equidistant from the top and the bottom, so your S1 equals to S2 equals to what? It is the ratio of I times that that C, that the distance of the maximum of the topmost or the bottommost fiber from the neutral axis. So it will be in this case H over 2, so that is nothing but B H square by 6 once you put that I equals to 1 by 12 base. So this is for the rectangular section over here. For the circular section, you have a similar kind of a formula that is there. So for the circular section, your I is equal to pi d raised to 4 divided by 64, right? And your distance from the neutral axis, the top fiber and the bottom fiber, is nothing but the diameter divided by 2, or the radius. So you get your S1 is equals to S2 equals to I divided by d over 2, which essentially leads to pi d cube by 32, right? So this is for the left one is for the rectangular section, the right one is for the circular section. Now is particularly no need to remember the section modulus at this particular time and this particular point. Later when you do design, it will be more helpful, but just remember that fundamental formula, and I will write it again just to bore you. So our overall the most important fundamental formula is sigma x equals to m y by I. This is the modulus I'm looking at, right? If it is positive, if you're looking at the the compressive stresses, it will be a negative sign. If you're looking at the tensile stress, it will be a positive sign. Simple. Now talking about the different the area moment of inertia different sections can have, these are the general formulas for that one, which you're quite familiar with. If you are not, I recommend you flip through some of the very basic standard textbooks in your +2 or any of the engineering or any of the mechanics of materials books. If you flip through the last pages in the appendix, you're usually given these bunch of formulas. So this is your IZ. So if you have a section on the Z axis, this is your IZ, what we just said, that IZZ, remember that it is integral of y squared dA, IY integral of Z squared dA. And also you will remember the parallel axis theorem, that if you have your I about the centroidal axis and if you have to calculate it about another axis, that is the I about the original axis, but area times that distance square. So you know these things. If you are unfamiliar, just go ahead and brush it up or look into the appendix. They give proper explanation in any mechanics of material textbook, and you will see that it gives a proper, for example, the book by Gear and Goodnow, Mechanics of Materials, it gives a very nice treatise of the review of the moment of inertia that is there. Now, as I said, within these books you will also see these kinds of tables which gives you for the different sections. Now you should be familiar with how to compute. If you get a odd section which is not rectangular, not triangular, not circular, not trapezoid, you should be in a position to calculate the moment of inertia for that particular section. So make sure you're familiar with that, right? So in the standard textbooks, you have all these different formulas. And the last thing which I'm going to say in this lecture, that remember that we talked about the section modulus for the different design sections. What you have over here are two very typical steel sections. Next time you go around, you take a look at steel structures, you will see there are several of these H sections or I sections and these channel sections which are there. And these pages that you see these are for the European standard channel, because this is a standard channel section, this is a standard beam section that you have. And for this, remember what I said, what you're mostly interested about is the section modulus S, and that depends upon the moment of inertia and the distance from the top and the bottom fiber. And if you see any of these tables, and this is just to give you an example, you're not going to particularly deal with some of this of these design tables, but just to give you an example of how this looks like. So for any particular channel section, see, it gives you what are the the different dimensions of the section, and also it gives you these guys. This is this S1 over here, S2 is sort of overlaid by this one, but you can see over here, see this S1 and S2, right? So overall, I hope that you are now familiar with the Flexure formula, which gives you a direct one-to-one correlation between the stress and the moment. And if you know the stress, you can backtrack and calculate the strain as well. So it is equals to, the stress is equals to my divided by EI, where the denominator EI is the flexural rigidity. Now we are going to take the Flexure formula and we are going to do a couple of example problems to clarify the concepts.